Hey there, and welcome to today's Explainer. I've got to tell you, I am absolutely thrilled to jump into this one with you because we are looking at a literal paradigm shift today. We're going to fundamentally rethink how we understand evolution, complex biology, and get this, even the way we treat cancer. For well over a century, we've looked at biology through a very specific lens. But, new research is forcing us to just completely flip that perspective on its head. And we kind of got to start right here. Survival of the fittest. You've heard it a million times, right? Fun fact, it was actually coined by Herbert Spencer way back in 1864 after he read Charles Darwin's work. And this single 19th century phrase has totally dominated our understanding of evolution ever since. It paints this really bleak picture of a fiercely competitive world where, the genetically strongest individual wins and the weak are just weeded out. But this brings us to a massive, really crucial question. Does survival of the fittest actually hold up when we look at modern oncology and just the sheer chaos of complex biology? Does it still make sense when organisms or cells are suddenly faced with entirely unexpected, completely chaotic life or death crises? Well, the short answer is maybe not. We're actually discovering that in a truly hostile environment, simple genetic fitness might not be enough to save you. So here's our roadmap for today's explainer. 1. Rethinking survival of the fittest. 2. Life in hostile environments. 3. The quick problem solver. 4. Chaos and trial and error. 5. Tumor progression reimagined. And finally, 6. New therapeutic implications. Let's dive in. Section 1. Rethinking survival of the fittest. Beyond individual strength. Now, neo-Darwinism was great. It brilliantly updated Darwin's original theory by adding genetics and our modern grasp of inheritance into the mix. But honestly, it still really struggles to explain rapid, massive evolutionary changes, what we call macroevolution, especially when organisms are just thrown into entirely chaotic, unfamiliar conditions. The contrast here is incredibly sharp. Classical Darwinian selection is all about individual fitness, reproductive success, intense competition, and basically waiting around for random genetic mutations to give you an edge. On the flip side, we have this newly proposed paradigm, functional selection. This focuses on collective adaptability, functional traits, cooperation, and rapid problem solving. It literally shifts the entire focus from the isolated individual to the cooperative group. And we really have to acknowledge that the classical interpretation comes with some pretty serious historical baggage. Interpreting survival as purely about the fittest was sometimes used historically to justify really harmful social policies, like eugenics, by pushing this false narrative of inherent superiority. And scientifically speaking, it created a massive blind spot. It made us falsely assume that competition is the only rule of law out there, which completely blinded us to the biological reality that cooperation is often an absolute necessity for survival. Moving on to Section 2, Life in Hostile Environments, when chance isn't enough. Think about it. What happens when organisms aren't just, competing in a nice, stable ecosystem, but are suddenly faced with an environment that is actively trying to destroy them? We need to define exactly what a hostile environment actually is in this context. It's not just having a tough day. Biologically speaking, it is an unexpected, chaotic setting full of novelty and complexity. And because it's completely new and incredibly complex, the organism has absolutely no known adaptation solution. It's just immense, terrifying unpredictability. So here is the absolute crucial point. If you are an organism in a hostile environment, waiting around for a random, beneficial genetic mutation to magically save you, that's basically a death sentence. Relying on the biological lottery of random chance, or even just throwing out random bet-hedging strategies, mathematically, it's just insufficient. It's way too slow. Simply put, if you don't adapt right now, you die. Which brings us to Section 3. The quick problem solver, navigating the biological maze. So if random mutation is too slow, how does life actually navigate this crazy maze? Well, back in 1969, Herbert Simon compared problem solving to searching through a physical maze. He noted that while it definitely involves trial and error, it isn't completely random or blind. It's highly selective. You try a path, if it doesn't work, you back up and abandon it. If you see progress, you push forward. What researchers are realizing now is that biological adaptation in these chaotic environments is exactly this. It's a rapid, selective, problem-solving process. All right, Section 4, Chaos and Trial and Error, the engine of innovation. If adaptation is basically problem-solving, the actual engine driving it is chaos itself. Here's exactly how that dynamic process plays out. Step 1. The organism senses immense environmental stress. Step 2. Because it doesn't know the answer, it launches a chaotic search. It tries multiple pathways and reactions simultaneously. Step 3. As it stumbles upon these successful little micro-solutions through trial and error, it integrates those into its memory without losing its prior knowledge. And finally, step 4. This allows for rapid behavioral switching. The system learns from its deviations and adapts on the fly entirely without needing a teacher to show it what to do. I really want you to take a second and think about why this matters so much. We usually think of chaos in biology or in medicine as a total breakdown, right? Like a failure of the system. But this framework suggests the exact opposite. Chaos isn't a breakdown. It is a deterministic, I don't know state. It's literally the primal order required to foster innovation. It's the only way a biological system can shake itself out of its normal routine to invent entirely new survival traits when its back is pushed against the wall. Let's look at Section 5, Tumor Progression Reimagined, Cancer as a Network. Let's take all of this and apply this complex systems framework to a very tangible, high-stakes example, tumor progression. We need to reimagine cancer, not as a bunch of isolated rogue cells, but as an interconnected network. When we look at a tumor microenvironment, which, by the way, is highly chaotic and hostile, especially when it's under attack by chemotherapy, we see cancer cells acting as self-organizing networks. This aligns perfectly with Stuart Kaufman's autocatalytic model, if you're familiar with that. The cancer population develops what are called group phenotypic compositions, or GPCs. They build redundant pathways, they share cooperative functions, they are literally prioritizing the collective resilience of the whole tumor over the fitness of any one individual cell. They're working together. So here is the massive paradigm shift, the real core takeaway of our explainer today. Tumorigenesis is not about the single strongest, most mutated cancer cell just outcompeting all the others. No, it's about survival of the quick problem solvers. The tumor survives because the cells collectively function as a rapid problem-solving network, successfully navigating the chaotic maze of our medical treatments to find a way to stay alive. And finally, Section 6, New Therapeutic Implications, Breaking the Solutions. Why does this theory matter so much to you and me? What are the real-world therapeutic implications of viewing cancer this way? Well, if cancer is a network of problem solvers, we have to fundamentally change how we fight it. The immediate takeaway here is that we need to target the network, not just the individual cells. If we recognize cancer as this cooperative, problem-solving entity, then our therapies should be designed to disrupt their functional redundancy. We need to attack those group phenotypic compositions, because if you disrupt their ability to cooperate and share solutions, you drastically reduce the tumor's collective adaptability and its ability to resist treatment. You essentially take away its ability to solve the problem of your medicine. I want to leave you with this really provocative thought. For decades, we have tried to kill the fittest cancer cells. But if cancer actually survives by collectively solving problems, can we finally cure it by simply breaking its ability to find solutions? It really challenges us to look at biological chaos, disease, and evolution through a completely new lens, one that just might unlock the next generation of incredible medical breakthroughs. Thanks so much for joining me on this explainer, and keep questioning the paradigm.